Before any formulas, 3 plain questions. If a staircase always hugs a straight rail, must the two finally meet at exactly the same height? Or could the steps drift apart forever? When can a whole pile of small overshoots and undershoots quietly cancel out? And could you ever settle an exact fact about the primes with nothing but counting and arithmetic? Now, the dark. You're climbing a long staircase, one hand resting on a smooth rail bolted right alongside the steps. Every step lands close to it. A hair above, a hair below, never straying far. Low down they come thick and fast. The higher you climb, the farther apart they spread. No lights. All you can do is feel one step at a time. Each step you feel is one thing you can count. One more prime climbed. Give that running tally a name. Pi of x. How many primes you've passed by the height x? That's the staircase, earned from plain counting, before a single formula. And both pictures move as one. Slide the marker x to the right, and the steps climb and visibly thin. Near a billion, you'd walk about 20 numbers between them. Thinning and widening are the very same motion. Then the quiet thought creeps in. By the very top, do the steps and the rail meet at exactly the same height? Or does the staircase forever just hover near it, never quite touching? Chebyshev tracked that gap to within about 1/10 back in 1852. Closing it to exactly nothing took another lifetime. And in the end, nothing but counting and arithmetic. Last week, the staircase climbed beside the rail in the dark. Now, a little light. Is there a formula the steps are secretly tracking? Let's race 2 guesses against the climb. Young Gauss guessed first. Privately, at 15. Primes thin out like 1 over a logarithm. Crudely, x over log x. Legendre nudged it, shifting the log by a constant near 1.08. Same shape, a hair sharper. Gauss's sharp guess, though, wasn't that. It was the log integral lie. Lay both over the staircase. Lie clings from just above. X over log x lags below, always trailing. Now measure the gap. Divide the step height by x over log xx. That's 1 needle. At 1,000 it reads 1.16. A million, 108. A billion, 105. Still 5% high. Crawling toward 1 from above. Lee's miss? About 1 part in 30,000. Far, far flatter. 1852. Chebyshev built a cage. The needle can never leave the strip. 0.92 to 1.11. It is right, and if the needle ever settles, it settles at 1. As a bonus, out fell Bertrand's postulate, a prime always hides between n and 2n. Hang on, that window is tiny. Pinning it to exactly 1 is just a rounding error away, surely. It feels that way, but no. The cage pins only the order. It says the needle stays inside, never that it stops. The needle is free to wobble between those walls forever, never settling on anything. Proving a limit exists is a different kind of claim. That gap? Not a rounding error, is the whole obstacle. One honest footnote. Lee beats the primes everywhere we can compute, but not always. Littlewood proved Lee slips behind, infinitely often. The first crossing weights past a number with 316 digits. So, right shape, gap shrinking. But is the ratio exactly 1? So sit with this. It matches every number we can reach, and the gap keeps shrinking. Is that the same as proving the ratio is exactly 1 forever? Our 3 questions are still up here. And this is the staircase we've been climbing. The prime count, all jagged, forever chasing that crude guess. It works. But it never quite sits still. So let's trade it for a smoother cousin. Start from what we already own. Pi just counts each prime as a 1. Now hand every prime a weight. Its very own logarithm. That gives Chebyshev's first count. One more move. Don't stop at the primes. Count their powers 2, 4, 8, 9, every one. Bundle the whole lot into a single clean weight, the von Mangold lambda, and out drops the second count. You might fear those powers pile up. They barely do. The whole difference is ruled by the square root of x, a thin sliver that simply vanishes against x. Now watch why any of this is worth it. Lay the second count along the line y equals x, where the old staircase swung wide. This one hugs tight, step after step after step. Put a name on the leftover gap. Call it R, the wobble. Down below, the old swing is enormous. The new one barely leaves 0. Same climb. Hugging the line is just R staying flat. Hang on though. Why abandon the primes I actually care about for this weird log-weighted thing? Isn't that just bending the question to dodge it? Fair worry. But no. Psi is the natural count, a clean sum of lambda, and those log weights are exactly what let Selberg's engine snap shut next beat. And we lose nothing, because the swap runs both ways. So pin down any one of these and the other 2 come free. One single fact wearing 3 faces. From here on, the smooth count is our real target. And remember the very first thing we asked. Do the steps ever truly meet the rail? Look. The new staircase hugs the line. But hugging still isn't meeting. Not yet. Our 3 questions are still waiting up here. Now we meet the engine that finally drives the whole proof. Selberg found one remarkable fact. 3 sums that look nothing alike. One running over the primes, one over the von Mangold weights. One folding psi into itself. And every single one of them lands on the very same place. But read that error honestly. The O of x is no crumb. It's an envelope as wide as one of the main terms itself. And that width is exactly what makes everything after this so delicate. Watch the 2 sums grow. As x climbs, both of them chase that 2x log x line and ride right alongside it, the gap never opening past that one fixed envelope. But where does that 2 even come from? It falls straight out of adding up the log squared. A little polynomial, u squared minus 2u plus 2. That middle term is where the 2 was born. Now the gem at the heart of it. Start with something you already own. The von Mangold weight times log n. A plain pointwise product. Bolt on its convolution twin. Call the pair lambda 2. Why bundle them like that? Convolve the pair with the constant one, using 1 star lambda equals log. twice over, the whole thing collapses to log n squared. Then invert with Mobius, and out drops a singly enclosed form. And here's what that closed form is really doing. Run across the divisors of n, weight each one by mu plus minus minus plus times log of n over d, all squared. Total them up, and you've rebuilt lambda 2 by hand. Hold on though. That first term, lambda times log n, isn't that just lambda convolved with log? Why isn't there a star on it as well? Sharp question. And it's a trap. Test it at n equals 4. Read that first term as a convolution and you get 0.961. But the true value is 1.441. Draw a star there and the identity is simply false. It's a pointwise product. You multiply. You don't convolve. One honest flag before we move on. Collapsing all of this down rests on one deep fact, that a certain Mobius-weighted sum equals 2 log x, give or take a bounded wobble. That single step is as deep as Selberg's whole formula. It's the part we cite, not prove. So keep just one line, 3 faces, 1 engine, and all of them point straight at 2x log x. Back to the staircase. The gap between it and the line psi minus x, that's the wobble we named last time, r of x. And the whole theorem now hangs on one question. Does that wobble we named last time, r of x, and the whole theorem now hangs on one question. Does that wobble shrink to nothing? So let's... Remember Selberg's engine? Its last face was written all in psi. That's our black box, earned 2 beats back. Now we feed it in. Now the one move. Wherever psi shows up, we split it. The straight line plus the wobble. Line plus r, all the way down. And here's the quiet magic. Mertens, that old running sum of the log weights, drags both straight line pieces onto Selberg's 2x log x, and they cancel. Gone. What's left stops you cold. Read it aloud. The wobble at x equals of the minus sign, the weighted average of its own shrunken copies. At x over 2, x over 3, x over 5, r on one pan, a whole pile of little r's on the other. The staircase is grading its own homework. Wait. Every copy, r at x over n, is smaller than r at x. And you're averaging a whole pile of smaller things. Doesn't that just automatically shrink it? It's the obvious hope. So let's chase it, honestly. Take sizes everywhere. The triangle inequality, the most honest tool we own. Call the very worst the staircase ever strays. As a fraction of x, little a. Then every single copy is at most a times its own x over n. We bound them all by the worst case at once. Mertens, one last time, folds that sum back into a single x log x. Divide through by x log x and watch the needle. A is at most. The coefficient comes back exactly 1. We've proved the wobble is no bigger than itself. Nothing. There's the wall. The triangle inequality quietly assumed the worst. Every copy maxed out, and all pointing the same way. Stack same-signed worst cases, and, of course, nothing cancels. This is the obstacle that held the whole world up for 45 years. Remember our very first questions? Stay within a hair forever, or actually meet? Now, we see why it's so hard. Staying close is easy. Meeting needs the wobble to die, and honest bounds alone refuse to kill it. So, if averaging is ever going to rescue us, the overshoots have to be paid back by undershoots. But why on earth should an overshoot here force an undershoot there? Last beat slammed us into a wall. The honest bound handed back the very number we started with. A is at most A, no shrinkage. So the rescue can't come from size. It comes from sign. Picture a seesaw balanced on the line. Say the staircase overshoots here, riding a hair above the rail. Selberg's identity chains every scale to its neighbors, so that overshoot can't just sit there. It gets paid back. An undershoot dipping below the rail nearby. Now average the two with their weights. A plus beside a minus, they eat into each other. The signed copies partly annihilate, so the average comes out strictly smaller than the worst case ever could. But cancellation only helps if the scales are there to cancel. That's Erdős. Inside any little window, there's always a clutch of primes, at least C of delta times x over ln x. And C of delta is times x over ln x. And C of delta is strictly positive. The primes never thin out enough to leave a hole. Now a hand goes up. Hold on. There's always a prime nearby. Already smuggle in the very theorem we're proving? Isn't this circular? And aren't you just asserting the signs cancel? Fair. On both counts. But no. The lemma asks only for a lower bound, and it drops straight out of Selberg's formula. Not the conclusion. The argument never bites its own tail. Fuse the two strands, sign reversal and Erdős. The weighted average drops below by a real discount. A minus C prime of A, positive whenever A is. And here's the honest half of that student's question. Yes. This fusion is the single hardest step in the whole proof. We're not deriving it. We're citing it. Feed that back into the self-averaging bound. A is at most a minus C of A. Subtract A, C of A is at most 0. But C is positive the moment A is. The only escape left is that A itself is 0. And A equals 0 is the whole game. The wobble R collapses to nothing. Lim soup and lemon both pinned to 1. The squeeze finally shut. So psi is asymptotic to x, which relates beat 3's chain. Psi like x gives theta like x gives pi like x over ln x. The staircase welds onto the rail. Remember the two questions we hung up in the dark? Do the steps ever truly meet the rail? Exactly. Not just nearby. They do. And can a whole pile of over and undershoots quietly cancel each other out? They can. That seesaw is exactly how. Two people. One. Selberg published the simula. Erdős, a key elementary step. 1949. Separately, after a hard falling out will leave even-handed. A Fields Medal followed for Selberg. And all of this, no complex analysis, no zeta, no contours. Elementary. Just, as we'll see next, not the same as easy. Watch the wobble die. For 45 years it was free to roam, a hair above the rail, a hair below. Now the squeeze pins it. The deviation can't help but fall to 0. And the instant it does, the staircase stops hovering. It welds, rung by rung, onto the line. And the chain we built lights up, link by link. Psi hugs x. So the log-weighted count theta hugs x as well. The prime power sliver between them just melts away. And undressing that, back through Abel's summation, the prime count itself meets x over log x. Exactly. At last. But let's be honest about what exactly buys us out in the real numbers. At a billion, there are 50,847,534 primes. Divide that staircase height by x over log x, and you get 1.0537. Still better than 5% too high. The limit is 1. But the crawl toward it is glacial. Now, trade the crude guess for Gauss's sharper one. The log integral, L, shadows the primes far tighter. At a billion, it misses by just 1,700. 0.003%. Against x over log x is 5%. But don't crown it. L runs ahead of the primes everywhere we can compute. Yet Littlewood proved it slips behind infinitely often. The first crossing waits past a number with 316 digits. And here's where a student always stops me. So elementary means easy. The elementary proof finally beat the analytic one? No. And this matters. Elementary means one thing only. No complex analysis, no contours, no zeta. The proof is long, intricate, arguably harder to follow. And historically, it gave a far weaker error rate than the analytic route had decades earlier. It's a different road up the same mountain. Neither replaced the other. Both proofs stand. Two roads. Both stand. Which answers our last open question. Could plain counting and arithmetic ever settle an exact fact about the primes? Yes. It can. Not simply. Not easily. But yes. 3 questions asked at the foot of the stairs. Now answered. The whole hunt, in one breath. Primes thin as you climb, yet their staircase clings to a straight line. For a lifetime, no one could prove they truly meet, until averaging steps against their echoes pinned it, by counting alone. And it spells the name of the man at its center. S, the staircase in the dark. E, the estimates that came close. L, the line hugger. Psi. B, the bridge of symmetry. E, the easy bound that died. R, the reversal that saved us. G, the grand payoff. SCLG. So one last question. And this one is yours. Not mine. We forced the staircase down onto the line. Yet Lee shadows the primes far tighter. And even it slips behind. First past a number with 316 digits. How close